In this video, we give a short introduction to hypothesis testing. Hypothesis testing is one very important mechanism for decision making. It is actually a technique from inferential statistics by which we try to obtain information about the value of a parameter. This parameter could be the population mean, the population standard deviation, or the population proportion, or whatever other parameters. So I think the best idea for explaining what is hypothesis testing is with an example. Assume a home building company wishes to test to determine whether the mean time to frame and roof a new home is 25 or fewer days. The standard deviation, sigma, is known to be 3 days. Assume we know that. We know what is the standard deviation. How can we check if the statement is true? How can we check if really the time that the company spent framing and roofing a new home is 25 days or fewer days? We have here a statement about the mean. And we would like to know if this statement about the mean time to frame and roof a new home is this 25 or fewer days. We know that in many cases the sample mean follows a normal distribution. For example, when the original random variable have a normal distribution, for example, in this case, the mean time to frame and roof a new home, if this time is normally distributed, then the mean of this time will be also normally distributed. So there will be some times when we know that the mean follows a normal distribution. And in this case, we also know the standard deviation of this distribution. So we know exactly the form of the distribution. So we know that the distribution will be something like this. There is one statement here that mean is less or equal than 25 that we want to check. So we want to check if this is true. So we have a hypothesis. If this is not true, then the opposite will be the true. So if this is not true that mu is less or equal than 25, then mu will be more than 25. So when we have a hypothesis like this, we have a different hypothesis that complete the whole sample space, yes, because actually the mu could be less or equal than 25 or could be more than 25. If this hypothesis is not true, then what is going to be true is the opposite. The mu is more than 25. If we know that the mean time to frame and roof a new home is actually 25 days, then we are going to know that the value that is here in the center of this distribution will be 25. So that will be the value here. And we also have information about the standard deviation of this distribution. If you remember, the standard deviation will be the standard deviation of the random variable divided by the square root of n. So a good idea to see if this is true is get a sample. I will get a sample and compute a sample mean. So what we are going to do? So if we want to check if this is 25 or less, then what I'm going to do is compute the sample mean. Obviously, the fact that the sample mean is different than 25 don't prove anything. For example, if I notice that the sample mean is 25.1 or 25.2, if the sample mean is 25.2 or 25.1, I can think that it could be false that mu will be less or equal than 25. But you know that the sample mean is a random variable. So it's possible that could be bigger than 25, even if the actual mean is 25 or less. So it's possible that this sample mean could be a number greater than 25, even if the actual mean is 25 or less. So the fact that the value of the sample mean is greater than 25 doesn't prove anything. The only way to prove that this cannot be 25 or less is that we obtain a number that is very far, very big. When I say too far to the right. So it's actually bigger than 25, but much bigger than 25. So if we need to decide from which value we are going to start believing that this mu is not less or equal than 25. So we are going to compute the sample mean, and we are going to reject this hypothesis that mu is less or equal than 25 only if the value of the mean is too big. But what means too big? How can we determine that the value of the sample mean is too big? One idea could be define a region in such a way that the probability that the sample mean falls in this region is very small, given that the value of the mean is actually 25. So we are dividing the area below the normal distribution in two parts. One part in which we are going to accept the hypothesis that the mean is less or equal than 25, and another region that is, in this example, located to the right of the distribution, in which we are going to reject the hypothesis that mu is less or equal than 25 if the sample mean falls in this area. This will be the area of rejection. Actually, what we are doing is assuming that this 25 is true. So actually we are defining a region when the probability of rejecting something that is true is very small. We call this probability of committing an error of this type is very small. An error of this type is called a type 1 error. So this will be the rejection region, and this rejection region will be a very small area. This alpha is called the significance of the test, and it's usually 0.10, 0.05, or 0.01, or whatever other number, but must be a small number. So we are going to compute x bar, and if this sample mean falls in the rejection area, we are going to reject the hypothesis that mu is equal to 25. And actually we are going to reject the hypothesis that mu is less or equal than 25 because we have choose this rejection area bigger than 25. So we are going to choose this rejection area to the right of this 25. And this will be a good idea of rejection because we have assumed 25 as a true value, and if this were true, the probability that x bar falls here will be very small because we have also choose this alpha as a small number. Let's make a hypothesis testing. Let's go there and compute this sample mean. So I'm going to explain a hypothesis test for mean with this example. I'm going to use a z-test statistics and observe that in this example we are assuming that sigma is known. I'm also going to explain why we call this test a one-tailed test. So the example, if I read it again, is this. A home building company wishes to test to determine whether the mean time to frame and roof a new home is 25 or fewer days. We know the standard deviation. The standard deviation is known to be 3 days. If a random sample of N64 homes, so now I'm taking the sample, provides a sample mean of 26 days, now I compute the sample mean, what conclusion should be reached? Is that happening? We are going to choose, obviously, we need to choose an alpha. Let's choose an alpha equals 0.1. So we have two hypotheses. One is mu less or equal than 25. And this is given here in this problem. We want to check if the time to frame and roof this new home is 25 or fewer days. So we know that there will be one hypothesis that mu is less or equal than 25. This hypothesis is called a null hypothesis and we symbolize at a sub 0. And you can recognize it because in this null hypothesis will be always unequal signs. We are going to assume that mu is equal to 25. The other hypothesis is called the alternative hypothesis. In this case, this null hypothesis is the research hypothesis. It's what people believe. What we want to determine is this true or not. So this null hypothesis, in this case, is the research hypothesis. So we are going to research this. The other hypothesis, the opposite to this null hypothesis, will be the alternative hypothesis. Sometimes this alternative hypothesis is the one to check if it's true. So sometimes the research hypothesis is the alternative hypothesis. How you recognize that this is the alternative hypothesis? Because it doesn't have an equal sign. Because n equals 64, we are sure that a normal distribution for the sample mean will be a good distribution. So we are going to use the normal distribution, and we know that this region of rejection is alpha equals 0.10. So this number is 0.10, and we are going to use the standard normal distribution. Well, we are assuming that mu equals 25, but this 0 corresponds in the standard normal distribution to this 25. So this alpha here, it will be 0.10. So that will be this area. And what we are going to do is to compute this z. You can use a standard normal distribution table and find which value of z divide the acceptance area with the rejection area. You can go to a table and find what value of alpha has 0.90. For example, if you have a table that have the areas to the right, find what value of z have 0.90 to the left. Or if you have a table that have only the areas until the center of the distribution, you can find what value of z have an area equal to 0.40. Because if this is 0.10, this one here will be 0.40. Because what I have here is Excel, so I'm going to use Excel, and in Excel you're going to type equal normal standard inverse of 0.90. Let's type it here. Normal standard inverse open bracket 0.90. Press enter and Excel is going to tell you the number 1.28. If you use a table, you can see that this 1.28 will be the area, will be the value of z that has 0.90 to the left, or the value of z that have an area closer to 0.90. So you have the value of z, you have this critical value, this value that separates the acceptance region to the rejection regions. And now what we are going to do? We know that the sample mean follows a normal distribution. And we also know that this 26 have a z-score in the standard normal distribution. So to check if this 26 is really far from this 25, far to the right, what we're going to do is compute the z-score of the 26. And if this z-score falls in this rejection area, we're going to reject the null hypothesis. So we are going to reject the fact that mu is less or equal than 25. So far we don't know if this 26 is in this region or is in that region. So this z-score of the 26 of this value of the sample mean will be what we call the test statistics. So we are going to compute the test statistics of this 26. Now remember, the z-score of the sample means will be z equal the value of the sample mean minus the population mean divided by the standard error of the mean. And remember that the standard error of the mean is given by sigma divided by root of n. X bar is 26, and use the value of mu corresponding to the one that appears in the null hypothesis. The null hypothesis said that mu could be equal to 25. So use this value of mu. So mu will be 25. So we are assuming that the null hypothesis is true, that mu could be equal to 25. So put here 25. Sigma is known to be 3, so put here 3 and divide by the square root of n, that is the size of the sample. And we know that n equals 64. So make a substitution, will be 26 minus 25 divided by 3 over a square root of 64. And that gives you 2.67. Because this 2.67 is greater than 1.28, so this 2.67 will be like here. Yes, this will be a number to the right of 1.28. This is 0, this is 1.28. 2.67 is more than 1.28, so it's in the rejection region. So because z is equal to 2.67, so greater than the critical value, so that was only 1.28, we reject the null hypothesis. Let's summarize what we have done and what we do anytime that we make hypothesis test. So this will be the step process of statistical hypothesis testing. The first thing to do is state the null and alternative hypothesis, A0 and A. So null hypothesis, alternative hypothesis. They must be a statement about one or more parameters. So it could be the mean, the population mean, it could be the population proportion or the population standard deviation or whatever other parameters, whatever other number associated to the whole population. So it could be mu, p, or sigma, or whatever other. A0, the null hypothesis must contain an equal sign. That will be important because we are going to assume that this A0 is true. And obviously, we want to assume something that we can substitute in the test statistic. So if we know is that mu, for example, is equal to something, this something can be a good substitution for the population mean. So we are going to assume that this is true. So the symbol that would appear in A0 will be the equal signs. Obviously, if you type less or equal or greater or equal, depending on the problem, will be okay. There will be an equal signs in the null hypothesis. In the alternative hypothesis, must has at least one statement without these equal signs. So there will be a statement where say greater than or lower than, so without equal signs. So it could be less than or more than or maybe no equal than. Whatever of these three signs is okay in at least one of the statements of the alternative hypothesis. When the alternative hypothesis have several statements, in this example that I already did, so we have only one statement in the alternative hypothesis. But later you're going to see that an alternative hypothesis will have statements sometimes about several parameters. Second, we need to set a significance level, so that will be alpha. So this is a small number that could be typical. For alpha could be 0.10 or 0.05 or 0.01. So these are conditions that alpha must have. It could be any other number, but usually lower than 0.10. But these are the most common. Then you go there and collect data from a sample. For example, if your hypothesis testing is about the mean, then you collect sample to compute the sample mean. And in any case, you are going to collect a sample for computing the statistics that estimate the parameter that you are testing. If you are testing the proportion, you are going to collect data to compute the sample proportion. If you are testing a hypothesis about the standard deviation, then you collect data to compute the sample standard deviation. 4. Determine the acceptance and rejection region, knowing that the area of the rejection region is alpha. So you're going to say, for example, that if the alternative hypothesis have a greater than, for example, mu greater than, then the rejection region will be to the right. So it will be, a rejection region will be something like here. Yeah? So this will be the acceptance, and that will be the rejection region. In this way. This alpha here, so this region will be, the size of this region will be alpha. If the alternative hypothesis say is not equal is because lower than a special value or greater than a special value. So it will be, the rejection region will be divided in two parts. When we are testing something like this, we call the test a two-tailed test. So the acceptance will be in the middle and the rejection region will be separated in two regions. So depending on the alternative hypothesis, you can decide if the region is to the right, if you see the greater, or is separated in two parts, or maybe is to the left of the distribution, a left tail test, for example, if the sign in the alternative hypothesis is less than. Okay, so what we need to define, what are the areas of rejection? And obviously, there will be a z, a critical value here, yeah, that separates the acceptance to the rejection region. When we are defining this rejection region, one possible idea could be compute the critical value, yeah, the value that separates the rejection region and the acceptance region. Then we are going to compute a test statistics. This test statistics could be, for example, a z-test, like this, x bar minus mu, divided by sigma root of n, if the hypothesis test is about the mean, and we know the standard deviation. But the test statistics could be t, for example, if we are making a test about the population mean, again, but we don't know the standard deviation. And we know if that is the case, we don't have a normal distribution, but a t distribution with n minus 1 degrees of freedom. Or maybe a z statistics, like this, when we're making a test about the proportion. But anyway, in this, and now we take a decision that will be based on step 4 and 5, based on these rejection regions and this test statistic, we are going to draw a conclusion about the null hypothesis. So if the test statistics falls in the rejection region, we are going to reject the null hypothesis. The conclusion will be a statement about this null hypothesis. And these are the ideas of a hypothesis testing. With this, I finished my explanation, and in upcoming videos, I will be explaining some examples of hypothesis testing. But for now, I finished this video with the explanation of what are the ideas behind a hypothesis testing. So thank you for seeing this video, and I hope you have learned something. If you think that this video has been useful for you, please don't forget to like. Thank you.